So I handed those back. I'll put up the answer keys as well as the two forms of the exam. Hopefully you can you've got which one that you had on the Scantron. If for whatever reason you don't, you can check with me, send me an email, talk to me after class. I've got all your kind of original exams. I keep those just to make sure that way I know which form you guys had. It's always kind of a double check. You can figure out which ones you got wrong and kind of see what those problems were. And if you want to rework them, you can kind of do that. So I'll have the answer keys up. So very quickly you can identify, which ones you got incorrect and then kind of go and look at the exams to see what the correct answer was. Okay. So we've got that current Connect assignment out there. We'll, should be able to get a pretty good ways through that after this week. I'll put up the next Excel assignment, which will look, at least the beginning will be things that we're doing today. And that will be due kind of after spring break as well. So we've got kind of a ways to go on those, but tackling the parts of that we can already do before spring break might be a good idea because, just get another week further removed from material, okay? Any questions from you before we kind of get going here today? I will also put up a online quiz after the class today, which is due before we start class Wednesday. A couple little questions, just kind of make sure you're starting, working through some of these, and it kind of gives me an idea of where we're at in terms of our understanding, okay? So, I threw in some old slides here from last week. These are some examples that we worked through. We got to the inverse transformation formula. I then kind of have this normal distribution in Excel slide, and this is, a good reference, but we'll kind of work through some of this just to even start out today. So we'll kind of work through a couple other problems as well as doing it in Excel. So if we go to Canvas, you've got under files, there's this in-class data folder. And actually, it looks like it's when I updated the file, but we're going to use this Indiana weather data again. Okay. So, oops, I've got two of them open. So I'm going to open up this Indiana weather data file. It's got a bunch of different tabs. So the first one I'm going to go to is just this temperature one. Okay. So I'm going to zoom in here. I've got something set so it kind of freezes these first two columns so you can always see the year. But basically, this was that weather data I was using last class. You've got every single month. You've got what the temperature was recorded in all these different time periods. So I'm going to delete some of this. So I'm going to get rid of these down here. And then I'm going to get rid of these. And we'll kind of rebuild this. Right? And actually, let's see here. Actually, we're going to relabel this August and this September just to make this a little bit easier. August, September. Okay. Maybe we'll be interested in 77 over here. So all I'm going to do is, first of all, if I wanted to find the average temperature across this time period, I'm going to go to this annual kind of column, Control Shift, hit the down arrow, hit Enter. And I've got the mean, right, for overall temperature. Now I can also find the variance, right? I'm going to treat this like it's population data, right? Since it's every kind of year. I guess I think I added some, should be not just 2012. Yeah, it goes all the way to 2019. So I can find the variance on the annual temperature by var.p, Control Shift, Command Shift on a Mac, hit the down arrow, hit Enter. Now, if it makes it easier for me to think about it, I can put the standard deviation right below it and just simply take the square root using the SQRT formula and take the square root of the variance. Like, these are things we've already done, right? So just using the average function, var.p to find the variance, take the square root of that to get my standard deviation. Now, the way I have this set up, I can also do this pretty quickly for different months. So notice for June, you can find the average, scroll over, select the June column, Control Shift, hit the down arrow. Now, one thing to notice here, sometimes there's stuff that's below the data set. So this is actually not a very good way to set up your data, kind of on this last row. I put the month number, right? So when I hit Control Shift or Command Shift and then the down arrow, it selects the entire data and then plus this additional row. Well, I don't want it to do that. So one thing you can do, just to kind of start out again, show you this little shortcut. I could do it. We'll go back, just have the average function. So I'll go back, select the very first cell in June. Now, I'm not going to take my fingers off Control and Shift or Command Shift. I'm going to hold those. when I hit the down arrow, when I hold control and shift at the same time, it goes all the way down to the last cell. There's something there. I'm then just going to take my finger off of the control button. So I'm just holding shift. Now, when I use my arrow keys, it's only going to move one cell at a time. So notice I can go up one cell or down one cell. Right? That way, when I hit control shift, it sent me all the way down to the bottom. But now just holding shift, I'm going to go up one cell. So I'm only selecting the data. Okay? Same kind of thing. If I'm just holding shift and I hit my overs arrows, like left and right, excuse me, it's only going to move one row. Well, if I'm holding control and shift, notice it goes all the way over. So I don't want that to occur. Just want to have selected that June kind of column, of data. I accidentally bumped something with my finger. Okay. I'll hit enter. I've now got kind of average June temperature. I can do the same thing. var.p. Go over with my arrows, control shift, command shift on a Mac, hit the down arrow, hold shift, go up one, so I'm not selecting that month number. Okay. Hit enter there. And then the last thing that we would kind of want, take the square root of our variance to give us our standard deviation. Now, because I've got the column set up so that it's like month after month, because these are in order, I'm just going to copy them over. That way it'll update the column and I'll be using July data for the next one. Then I would have been using August data and September data, et cetera. Okay. Questions on this? Hopefully, at this point, now it's like things we've already done. We've already done all this stuff in Excel, nothing crazy. So now we're going to figure out how do we use Excel and the standard normal distribution or the normal distribution. So we'll do it kind of the long way first, and then I'll show you a shorter way. Okay. So first thing we could do is kind of like we did this by hand. So let's do June temperature, and I've got my cutoff being 71.4. Okay. So I'm going to try to draw something as I talk through this, as big as possible. So I've got June temperature, which we said temperature follows pretty close to a normal distribution. And it's going to be centered around whatever that mean is. And I found the mean was what? 70.8. If I want to know what's the probability that it's 71.4, right, or anything below that, okay, well, then I need to turn this into a standard normal distribution. So I can convert that 71.4 into a z-value, look that up in the table, and find the area to the left. How do I do that? Well, my z-score was just take that x value, subtract the mean, and divide by the standard deviation. So all I'm going to do here is use Excel to do some math for me. So in parentheses, take my cutoff value I'm interested in, 71.4, subtract that mean temperature, and divide by my standard deviation. Okay. So I'm just using Excel to be like my calculator to find me my z-value. Right? So I get about 0.24, right? So not a very large z-score. That means it's only 0.24 standard deviations away from the mean, okay? Which kind of makes sense, right? I'm like not even 1 degree away from the mean. The standard deviation is 2.2, so I'm like about a fourth of a standard deviation away. So I've got my z-score. What I usually would do at this point is look that up in the table and find the area to the left, okay? Instead, in Excel, it's basically like it has this equator, this table built into it. If you use the norm.s.dist, right? So norm.s.dist means tell this function a z-value, it's going to give you that cumulative probability or tell you the probability of seeing that z-value or anything below it, which is exactly what the table did. It's just that the table is constrained to 2 decimals. Here, I can select a z-value out to whatever decimal level I want. And then comma, is it cumulative or not? So I don't know why they give you an option not to make this cumulative. I think what it does is finds a really small, or I think it finds the probability of an interval of 1, right? So like if I were to tell it, what, 0.28, it's going to like look over a unit of 1 from that z-score above, or I'm not exactly sure, because if I'm not making this cumulative, what should that probability density function of one specific value be? So that's kind of this counterintuitive thing where the probability of any one value is 0. The probability over intervals can be positive, but the probability of any one value was 0. Okay, so you have this kind of weird counterintuitive result. So we'll never not make this cumulative. So you'll always be putting a 1 there for the second thing. You're making it just like the table. It's always going to be finding the area to the left. Okay. So the area probably seeing a z value of 0.24 approximately or lower is about 0.59. Okay. Now I could look this up in the table. So let's say I had this z-score and it was what, 0.24 if I have to round to the second decimal. So I go to this table, I'm looking at the z value of 0.24. So I scroll down, 0.2, 0.5948, which 0.59444. I can be a little bit more precise with Excel because I don't have to round to that second decimal. But it's doing the same thing as using that table to look up z values. Okay. Any questions on that? Does that make sense? It's not too bad, I don't think. So norm.s.dist works just like you're looking up a z value in the table. Now I could copy this over and do this for several different cutoff values in different months. So, you know, what's the probability that the average temperature in July is 80 or below, right? Well, I'm going to guess it should be a relatively high probability because the average temperature is 80 or anything below that. So I get that it's 2.2 standard deviations above the mean. So when I look at the area to the left of that, it's about 0.98. And then let's look at August and September. So this is something kind of, I think, makes a good point. So notice the same cutoff of 77 degrees, right? Well, in August, the average temperature is 72, so it's only 5 away. However, in September, the average temperature is 66. That's almost 11 away. So we're going to be much further from the mean. Now, the standard deviations are a little different, but they're both approximately 3, right? So here, 77, you know, I don't know, it's about what, 4 away. So, I mean, I'm about 1.5-ish standard deviations. Sure enough, I calculate the z-score, it's about 1.4. Right? But that same cutoff value of 77 is going to be even further from that mean in September. So there we get that it's 3.3 standard deviations away from the mean. Right? So seeing an average temperature of 77 or below in August should be a lot less, you know, likely, or in terms of, if the average is 73, seeing 77 isn't that unrealistic, right? So the probability I see 77 or below is only about 0.92. Well, as of September, I mean, if the average temperature is 66, well, then what's the probability I see the average temperature be 77 below? Well, it's almost a guarantee. Sure enough, that probability is like very, very close to 1. So we can think about how the same cutoff, right, would alter the probability of seeing that value depending on what your mean is. You can kind of see that across, and that makes sense. You know, like if I got down to December, what's the probability that the average temperature in December is 77 or below? I mean, that's got to be 100%. I mean, it's almost impossible for us to see an average temperature in December be greater than 77. Okay. So I'm going to move this guy down a couple. So one thing that we might be interested in, kind of the way that I was just talking, is it makes a little bit more sense maybe to think, well, what's the probability that we see the average temperature be 80.1 in July or higher, right? That makes maybe a little more sense the way we talk. What's the only other step I need to do here if I want to find the probability of being greater than a certain z value? Yeah, just 1 minus, right? So I could find the probability of being above all of these values by simply doing 1 minus. And now it starts to make a little more sense, right? What's the probability the average temperature in August is 77 or higher? About an 8% chance. What's the probability it's 77 or higher in September? Well, there I'm down to, you know, what? 0.05% chance, right? Pretty low probability you saw the average temperature in September be that high. Okay. Any questions over anything that I've kind of done or set up to this point? Yep. So if I want the probability of being above a certain z value, I can't use the norm.s.dist to find that. That will always only give me the area to the left, or the probability of seeing that z value or anything below it. So if I want the probability of being above a certain z value, I can use that norm.s.dist to find the area to the left, and then just subtract it from 1. Because I know the area under the curve is 1. Remember, what I'm doing here is with that norm.s.dist, Where did I put my marker? Here we go. Norm.s.dist is telling me this area, right? The area to the left of that z value. If I wanted the area to the right, it was just 1 minus that. And I don't have to break this down into 2 cells. I could do it all in 1 cell if I wanted to. So for instance, I could do norm.s.dist, my z value, comma 1, and I get the exact same value. Right? So kind of, I can do it all in 1 cell, or I can kind of break it down step by step. Any other questions up to this point? So it makes I kind of find this easier than using like the physical table. I think it's easier to use the built-in. Now it's not like what Excel's actually doing. It doesn't have the table like stored in there. It's actually doing the integration, right? So it's actually doing the work that people did to build the table. So one thing that you could also do is use a shortcut, right? So instead of using Excel to be a calculator and finding the z-score, I can actually just use the norm.dist function. So what that does is it says, okay, look, I have this random variable x, and it's just normally distributed. I want to find the probability of seeing a certain cutoff value, but I don't want to see any of the intermediate work. So you can calculate the z-score behind the scenes for me. You can look it up in the table. Just tell me the probability of seeing this specific cutoff value for x or anything below it. Because remember, that's really where we were starting out. What we originally want is, well, what's the probability we see this certain value for x or anything below it? We then converted that into a z-score and then looked that z-score up because we know it corresponds to the original x values. So when I use just norm.dist, I'll first tell it what's my cutoff, right? Comma. Second thing I tell it is what's the mean. Here's June's mean temperature. And then comma, what's the standard deviation for this normally distributed variable? Here's my standard deviation. And then once again, the fourth thing, we're always going to make it cumulative. We're always going to tell it, find me the area to the left, okay? So this is going to calculate that z-score behind the scenes for me. It's then going to look it up and return to me the probability of seeing that z-score or anything below it. So I should get the exact same values. It's just that I've kind of cut out some of the middle, like the middle work. Right? Sure enough, I get the exact same thing. If I copy it over, I'll find the exact same thing for the other ones as well. Okay? So just using that norm.dist, it does all the work behind the scenes for me, okay? Any questions on that before we keep moving? I'm gonna see something again, or what if something changed, or? Yeah. So that's where, okay, so a good point. So it would be great and make a lot of sense if that's what that fourth thing, that function did. If I put a 0 here, so let's follow this idea out because this is good. So I know that if I want the probability of x being greater than a certain value, it should just be 1 minus this, right? So it should be about what, 0.4, just over 0.4. We've got that up here. Notice if I put a 0 in here, again, like I said, it's like doing an interval, like a small interval around whatever x value you're using. It's not really interpretable or usable to us at all. I have no idea why that's even an option in the Excel function because it's just not useful. It would make more sense if that last argument was a 1 to look for the area to the left or a 0 to find the area to the right, but it doesn't. It's not how it works. So we will always, in that norm.s.dist and the norm.dist, the last thing will always be 1. And then from there, if we want to find the area to the right, it's just 1 minus that. Right? That's the best we can do with what's been programmed into Excel. Any other questions? Yeah, if I program this, I would do that. That makes way more sense to me. But any other questions there? Okay, so that's how we can use Excel to, if we have a normally distributed variable to find the probability of being above a certain value, below a certain value. What if I wanted to find the probability of being in between 2 values? So maybe I want the probability, I don't know. Let's say, the probability of being in between 65 and 7. Okay? So I can do this all in 1 cell. right? If we remember kind of visually what that would look like, if I want the probability of being in between two values, let's call it A and B. What did we do? Well, we turn those into z-scores. I had a z-score for A, the z-score for B. I would then take the area to the left of that z-score of A. Another color here. I then would look up that z-score and find the area to the left of B, subtract the smaller from the larger one, and I'd have what's in between. So I can use that z-score equation, or that norm.s.dist twice, subtract the smaller from the larger, and I'll be done. Now, I'm not going to do all the intermediate work because I know that I've got this norm.dist function that does it all for me. So here I'm just going to think about this as norm.dist. So the first thing I need to find is the area to the left of my larger value, right, which is 70. Right, so the area to the left of that B value. So I'm going to say, okay, 70, comma, we'll use June. So we've got what? Oops. I want to try to keep this all in the same thing. There we go. Here's June's mean temperature, comma, here's June's standard deviation, comma 1. So that'll give me the red area, the area to the left of that z-score for B. I then want to subtract from that the area to the left from my z-score for A. Well, how do I get that? Norm.dist, 65 was that lower value, comma, here's the mean for June temperature, comma, here's the standard deviation. It's always going to be cumulative, so comma 1. Now I can break this up into steps, like I could have found these in different cells, or I can do it all in one line. Right? So what this does is that first norm.dist function gives me that red area, the area to the left of B. I then want to subtract from that this shaded green area, or the area to the left of A. So to find that, I use that norm.dist function, plugging in that lower value for A, which we had was 65. Right. So we can kind of use that normal distribution just like we would do some of these problems by hand. Okay. Any questions on this? Okay. All right. I want to show you. So I think the next thing we'll do, we'll stay in Excel. So this is kind of helpful. One thing we did also was the kind of inverse transformation. So I'm going to get rid of these guys right here. Okay. So there's a couple different ways we can do the inverse transformation. So remember, the inverse transformation was when we start out, like knowing the area we want, we look this up in the middle part of the table, find the corresponding z-score, and then back out what that cutoff value was for our original variable x. Right? So we're working in reverse, okay? So this first one, we can kind of do it just like we did in class. So we wanted to know what that test score cutoff was for that 90% cutoff. Right? So what I can do there is I'm thinking about, this is almost like a review of what we did last class. Sorry, z-value. I want to find the z-value that is a cutoff for the 90th percent, better than 90% of the other test scores, or we say kind of worse than 10%. Right? So that's going to correspond to a certain z-value, which would then correspond to a certain x value up here, right? In our inverse transformation formula, we said was this. So once I find that z-value, as long as I can find the mean and the standard deviation from the data, which we already did, all I need to do is look up that z-value. Right? So by hand, what we did was we said, okay, go to that normal table, find the probability of 0.9. The closest we can get looks like is between these two values. So 1.28, 1.29 will be our z-value. We'll use the higher of the two, 1.29. We'll see in Excel, we can do the exact same thing, but it'll be a little bit more precise. So maybe I want to find the z-value, right? That is the cutoff for 90%. So I'm going to use the norm.s.inv. So that tells Excel, I want to work in reverse. So I'm going to tell you the probability, and I want you to tell me the corresponding z-value. Before, we were telling it a z-value, and it gave us a probability, right? So we're working in reverse here. So the probability I wanted was what? 0.9. And actually, here, I'm going to select this reference so I can show you, like, quickly change it, right? So this is not 0.9, so let's change that to 0.9. And sure enough, we get a value that's in between 1.28 and 1.29. But we can be more precise. We don't have to like round to the second decimal. Okay? So if I find the same value kind of I would in the table, it's just that here I don't have to round it. I can be a lot more precise. Okay? Now from there, right, we could just use, okay, well, now I've got my z-value. So the inverse transformation is take the mean, add to that the standard deviation. Well, I've got the variance, so I can take the square root of the variance here. That's my standard deviation. And then just multiply that by that z-value, right? That was just coming from our inverse transformation formula. Once we find that z-value that corresponds to the probability we're interested in, just plug it into that equation. Okay? And there's no like built-in equation. We just have to use Excel to be our calculator. Okay? Any questions on that? So that's kind of working in reverse. Now there is a built-in equation if I just want to skip the middle part, right? So just like norm.dist kind of did all the work for us behind the scenes instead of using norm.s.dist and then having to see the z-value between, we kind of skip all that. If we just use norm.inv, so no s, that tells, okay, it's not a standard normal distribution anymore. I'm not giving you z-values. I'm using just a normally distributed variable x. So the probability I'm interested in is up here, it's at 0.9, comma, here's the mean of this normally distributed variable, comma, the standard deviation is the square root of the variance. So I can put functions inside of a function here. And, it probably would have made more sense if I created like another cell and just put the standard deviation there. That way I could just keep clicking it. But if I didn't, right, I could just take the square root of that variance, and that's my standard deviation. And then that's the last thing that it needs. So what it then does is it takes that probability you wanted, 0.9. It finds that z-value of 1.2815 behind the scenes, uses the mean and the standard deviation, plugs it into my inverse transformation formula, and is going to spit out at me what this cutoff value for x that corresponds to being the 90th percent cutoff. So I should hopefully get the same thing as I did down here. Sure enough, I do. Okay. So it's just kind of a way to kind of avoid a little bit more work. The only nice thing about doing it this way is you can kind of see what the intermediate steps are. Okay. Any questions there? If I set this up with a cell reference, now instead of, maybe I want to change this instead of 0.9 to 0.4, like the problem we worked through in class, it updates everything and kind of gives me the cutoff test score that corresponds to seeing 0.4 in that lower left tail. Okay. Any questions here before we keep moving? All right, so where are we at in time? All right, so we went through that. So that's kind of a start to how we're going to use the normal distribution in Excel. I think I'll hold off and show you this at the end. Let's see if there's any. So some of this stuff, these are just different values. We worked through a lot of this in Excel, the inverse transformation. Oh, start talking about sampling today. I'll return to that example at the very end. So, so we're going to transition a little bit, right? So hopefully at this point, we kind of understand a little bit more about the normal distribution, the standard normal distribution, how we do it in Excel. Okay. So we're now, like up to this point, everything we've been thinking about was like some normally distributed population data. Right? So that's why like in Excel, we were finding the population variance. We're assuming that we have some type of population data here. If we don't, right, we're going to have some issues. Okay? Well, not necessarily, but what we would like is once we start only having sample data, that we know that it comes from a normal distribution as well. Right? And so we have to kind of think about some things that need to be true in order for us to be able to treat it like a normally distributed variable. Okay? Before we get to that discussion, we'll talk about just making sure that we have a good sample. Okay. So the idea of having a good sample is that, I'll just leave this up here, that we have a sample data set that mimics the population. So think about it this way. If I wanted to know what the average height of the US population is, I then go out and it's just easy. I'm in the gym and I see a bunch of people standing there and it happens to be the Ball State men's basketball team. If they're my sample, then when I look at that sample mean for height, it's going to be way different than the population, right? Because A, I've just over-selected a certain group that I know is taller than the average population. Right? So I need to make sure I've got this random sample. So I can do it in two ways, right? I've got infinite and finite populations. What we're going to deal with is only finite populations, right? There's a finite number of companies. There's a finite number of people. There's a finite number of countries, right? If you start dealing with like an infinite population, which is like you can imagine if there is some data generating process that's just continuously churning out new observations, I technically have an infinite population. But we're not going to deal with that. There's a couple other issues that would bring up, but that's kind of outside the scope of this class. So we're going to be dealing with a finite population. So a census would be possible, but a lot of the times not plausible, right? We've already mentioned a little bit in the I think way earlier in the class, that these censuses are really expensive and sometimes they're not practical. Right? For instance, if I wanted the measure of weight in the US, by the time I get everybody's weight recorded, a lot of them have probably already changed, right? So we're kind of stuck with this process of I'll get sample data, I'll look at the statistics that come from that sample data, and then make inferences about the population. Now that only works if my sample looks like my population, right? If I've got like a sample of only Ball State, men's basketball players, and I'm trying to look at the height of the whole population, I've got an issue, right? So how do I make sure that my sample looks a lot like my population? So, so we'll call this random sample. It's going to have a size. We'll call this lowercase n. We've kind of already discussed this, right? And then the population size would be capital N, right? So our sample size will always be kind of smaller than the population, right? Now you can do sampling with or without replacement. So with replacement is the idea. Let's say I wanted to randomly sample 5 students from this class. Put everybody's name in a hat and I draw out a name. Write that down. Put it back in. I draw out another name. Write that down. Put that name back in. Draw another name. So if I do that and I'm just selecting 5 students, but I'm replacing the name every time, what could happen in my sample of 5 people? I could end up with the same person twice in my data set, right? So doing this with replacement more often than not doesn't make sense, because why even risk ending up with the same person twice in my data set? Because the reason I don't want to do that is now every person is treated as like one observation, except that person will carry the weight of 2 people, right? So whatever their measures, if I'm looking at average height, their height is going to carry twice as much weight. I want everything to be equally weighted here, right? So usually without replacement is better. So I say it is better. There are situations where you may not want to do that, but really outside the scope of probably any issue that we would deal with in this class. Okay. So without replacement makes the most sense. That way we don't end up with repeated kind of observations in our sample. I'll skip this because like I said, we're not going to really deal with infinite populations. If you did, like I said, we'd run into a couple other issues. We'll punt on this because we're not going to use this. And this is, 99.9% of the cases we'll look at, you would have a finite population anyways. Okay. So the idea that I want to introduce is this idea of stratified random sampling. Okay. So stratified random sampling is I'll take my population and I'll divide them into non-overlapping groups. So the best example I can give of this, and you could use, we'll keep going with height because this makes the most sense. I know that the population as a whole is about 50% male, 50% female, right? We could argue about the little bit difference, but it's about that, right? So maybe if I'm interested in the average height in the US, I want to make sure my sample is also 50% male, 50% female. Because if it's not, and I know that that characteristic of gender is linked to height, well, then my sample may not be reflective of the population as a whole. So what I'll do is if I want a sample of 100 people, I might go out and randomly sample 50 women and then go out and randomly sample 50 men. Then put those 2 random samples together to get my full sample of 100. Now I've ensured that that sample is evenly represented by the genders, right? Or maybe I'm doing something like with age, right? Maybe I want to know like average income. Well, I know income varies wildly across the different age brackets. So maybe I want to make sure I'm sampling, 10 people from every single age bracket, right? So 10 people from 20 to 30, 10 people from 30 to 40, 10 people from 40 to 50, so on and so forth, right? That way I ensure that my sample has kind of like an even distribution of age. Now, it just depends on the situation, how you would want to stratify the data, but those are some examples, right? So I've kind of already selected, we call them stratum, but really just think of you're separating them into groups based off of a characteristic will influence that variable that you're interested in. And so you want to make sure that your sample is reflective of the population as a whole. You can imagine maybe like in a lot of situations, you'd want to make sure that you did this with race, right? Or something where you want to make sure your sample, the percents of each race that's represented looks very similar to the percents in the population as a whole, right? So, you might make sure that, let's say whatever your percentages are, if I want to sample of 100 people, and let's say, I don't know, let's say like 50% of the I don't know exactly the numbers off the top of my head, but like 50, 60% of the population is white, then maybe I make sure I get randomly sample 50 individuals who are white, then I randomly sample, 15 people from a minority group that has 15% of the total population, right? So that way I'm ensuring my sample matches up to the demographics of my population as a whole. So we see this done a lot, and usually it's based off of some kind of characteristic that we know influences that variable that we're interested in. So I've given you a couple of them, but like a lot of the times you'll see this done with age, gender, maybe income brackets. I want to make sure that I have every income bracket equally represented or represented as much as they make up of the population. I could use stratified random sampling. Okay. So this is a really popular technique to ensure that our sample is looking like our population. We'll also kind of use cluster random sampling. This is really the same exact thing, except for we're going to be kind of creating these clusters or these subpopulations that look very representative of the population as a whole. So let's say, and I'll try to give it an example that really gets at it. So maybe I'm just interested in, income in big cities, right? So instead of looking at every single person in a big city and kind of sampling them, maybe I'll just create these clusters, or I'll look at the top 50 big cities and I'll randomly sample 2 people from each one of those big cities, right? Each big city is kind of like a subpopulation or a representative scaled version of the population as a whole. Like each large city represents every large city in the US. And so maybe I do something like that. Now this is a little bit different because I'm not necessarily stratifying my data based off of a characteristic about the observations, but I'm looking at, here we're going to see, right, I'm looking at different regions, right, or different areas. So maybe I want to do something like make sure everyone's equally represented of states. So like cluster random sampling would be I take each state, randomly sample 2 people from each state, then throw them all together. I'd have a full sample of 100. So it's still the idea that you're randomly sampling from like different groups and then throwing all those together to get your full sample. It's just here, each group is not defined by a characteristic. The groups are just usually geographic locations, right? So you're ensuring that you're kind of having a smaller scale version of the population in each one of those geographic locations. Okay. I think that's all I have here. Any questions on this before we keep moving? Very similar idea. And you probably won't do a lot of this since we aren't doing like any sampling or surveying here. But if you were doing some type of a survey, you'd want to kind of maybe make sure that you're doing something like this so that your sample matches up to your population. Okay. So they do this a lot with political polling to like ensure that you're getting different areas or different regions of the US represented equally, or at least represented by whatever percent of the total population they make up. You see them do this a lot with political polling. Okay. I think we'll start with that on Wednesday, but I do want to go, through one more thing. So just kind of I guess, I don't know, an aside that anytime you're interested in a variable, if it looks normally distributed, you can like do any of this. Like we've been doing Indiana weather today, but like one time I got interested. So what would this been, 2016 or 17? So the Cubs, if you look at like the number of wins that gets first place in the Central Division in baseball, it's pretty close to a normal distribution. Now, it's not truly continuous, so this isn't a perfect example, but even with a non-continuous variable, as long as it's close to a normal distribution, we can apply the normal distribution to it and come up with these probabilities. So I was interested in this because I think it was in 2017, they had like 97 wins, and I think they ended up in third place, right? Which is a lot of wins in baseball. Usually that would be enough to get you first place. In fact, the probability that if you got 97 wins or fewer, that you would get first place would be about, sorry, actually, I think it was 97 wins or greater, right? Because I then subtracted that from one minus 0.43. We actually end up with a pretty high kind of probability of seeing that. When I looked at the number of wins that got teams third place, so I found like the mean number of wins for the third place team in that division. I then found the standard deviation in wins. Well, I know if it's normally distributed, I've got the mean, I've got the standard deviation. I can turn that value of 97 into a z-score and figure out that if a team won 97 games or more, what's the probability they would end up in third place? And based off of the mean and the standard deviation, there's actually like a 0.003% chance. Like I forget how many standard deviations away from the mean that was, but it was a large number. I think that the average number of wins for third place was something like high 70s or something like that. So very unlikely. And this is just some weird random scenario, some dumb sports scenario where I was interested in finding how likely or unlikely was this to occur. And if the variable just happens to look normally distributed, well, you can apply that normal distribution to it, use that norm dot dist function like we were today with temperature, and find the probability of being above or below certain values. Okay. The other thing I wanted to show, and I was having another discussion last week with a professor from a different university about how important Excel is. So I know, once again, that you probably don't love all of this, but it will be very, very beneficial for you. He was talking as well about their advisory board. So some of their alumni kind of saying, you know, anytime someone can say they have any experience or not even a mastery, but just some ability to work with data in Excel or some other program, that's a huge positive. So just kind of showing you the power of what you can do. And we haven't really done anything up to this point, and I won't necessarily expect you to do this. Just making you aware that you can in Excel. So we had that standard normal table. Well, if I can find these cumulative probabilities in Excel, I can actually build that table myself. Imagine here I just use the norm dot, where is it? Norm dot dist function for the z-score of negative 3.9, I could get that probability. Use that norm dot dist function for negative 3.8, I could get this probability, but I can be even more precise, right? So what I did was, every time I want the combination of whatever my row heading is, plus whatever this column heading is, right? So negative 3.92. But then in the middle, I'm just using that norm.dist function. Now the problem is, when it's negative, I don't want to add 0.01, I want to subtract it, right? Because it should be negative 3.91, right? A little bit lower. So I kind of set these if statements up so that if it was negative, I was like subtracting the column heading because it's actually a negative value. And if it's positive, I'm just adding that column heading. So if I go across this row, it's going to continually take negative 3.90, negative 3.91, negative 3.92, and then use that norm.dist function, norm.s.dist, sorry, I'm using z values here, to find the area to the left of the cumulative probability. But notice I can freeze some of these things because as I move this across, I want this to stay the same, but I wanted this to update. So you can use combinations of freezing cells, like I can only freeze the column or I can only freeze the row. So when I did all of this, just delete all this, I only typed this in one time. But the way that I froze my row and column headings, when I copied this over, notice when I go to like a z-score of 0, I'm getting exactly 0.5. The probability is increasing as I get closer and closer to these higher z values. By the time I'm up to 4, my cumulative probability is almost to 1. Just like here, if we look at this one, z-score of 3.9986, z-score of 3.998. It's rounded, right? The other one was 0.865. So this is constrained to 4 decimals, so it has to round it up. But you could essentially build your own table. Now, I would expect you to like use these if statements and freezing these columns. But I like to try to give glimpses of kind of the power that we really have in Excel, and that we're really only just like scratching the surface in this class is with what you can do statistically. Okay. All right, so look for that online quiz that'll be due before we start class on Wednesday, as well as the next Excel assignment. You can kind of tackle the first problem on that. The rest of it we really won't talk about probably until we come back after break. Okay. All right, I'll see you guys on Wednesday.